Hi, I'm Gena. Today, I'm going to be walking you through how to prepare a PDF for semantic search workflows. In this exercise, we're going to take a PDF, extract the text, chunk it, compute embeddings, and then we're going to be all prepared to perform semantic search workflows in tools like AIP Logic and AIP Agent Studio. Before we get started, a quick word from our founder.
Discover how Palantir customers unlock more value from Foundry and AIP thanks to our live instructor-led trainings. We are Ontologize, a group of former Palantir engineers who love teaching. We've trained thousands of Palantir users at leading organizations around the world. Unlock the full potential of your Palantir deployment by going to ontologize.com.
For our work today, we're going to be using this document from the FAA, the Pilot's Handbook of Aeronautical Knowledge. So this is a handbook from the FAA, from the U.S. Department of Transportation, that tells you essentially everything you want to know about flying. We're going to be taking this document, parsing its text, chunking the text into smaller pieces, and then computing embeddings. So go ahead and find this PDF. You can find it just by searching for it. And now we're going to hop into Foundry and start building. So here we are in Foundry. You're going to hit Control-J, and you're going to search for Pipeline Builder. Click on Pipeline Builder. You're going to hit New Pipeline, and call this one your name in case you and some colleagues are doing the same work on your stack. Prefix it with your name. Gena, compute embeddings from FAA Handbook. Hit Select Location. Hit Browse to find your project, some project that you're doing work in. For me, it's my Palantir Learning project. And hit Save. You're going to hit Create Pipeline. And now we're ready to go. You'll notice we did not yet upload data, but we can upload the data right from Pipeline Builder, so we're going to do that. Once you're in Pipeline Builder, of course, make sure you've downloaded the FAA PDF. Hit Upload from your computer. Choose from your computer. It's going to be this FAA PDF. Click on it. Hit Open. Be very careful that you upload this to a new media set. And hit Next. For now, the primary media format is a PDF. Keep the write mode transaction list and hit Upload. Take a second while this uploads, and then we're going to get started. You're going to see that your upload finished. It's going to be called something like media set with the date. We'll change that later. Hit Done. To rename it, you're going to right-click on it, hit Rename, and rename this to FAA Document. That's first step. Now that we've uploaded the document, it's time to extract the text. Before we extract the text, let's look at it. If you click on the preview of the media here we have the PDF. One thing to note about this PDF is it is machine readable. And we know that it's machine readable because we can highlight the text on the page. You can see it's about 500 pages, long table of contents. We might not want to include that in our extraction. Lots of text here to work with. Also some tables. Generally for tables, you'd want to do something specific with them. So we'd want to do layout aware extraction. But for these purposes, we're generally going to ignore the tables. Click on the FAA document node. And you're going to hit Transform. So click Transform, and we're going to label this one Extract Text. The transformation that we're going to do, you're going to search for PDF. There's a couple of options for when you're working with PDFs here. For this case, you're going to hit Extract Text from PDF. For the extract method here, to keep it simple, we're going to use raw text. Raw text is appropriate for when you have a machine-readable PDF. OCR, or optical character recognition, that's for if you have a scan of a PDF, if your document is not machine-readable, or if you have text that's stuck in an image. Layout aware, that's for if you want tables, images. First thing is we have to specify the media reference column. You might be surprised to hear us talk about columns when you keep in mind that the input data is a media set, which doesn't actually have columns. So why are we already talking about columns here? If you click on media reference, you'll see that there are 3 column options. What Pipeline Builder has done for you under the hood is essentially converted the media set into a table. So we're accessing those columns. Under media reference, you're going to hit media reference. That is essentially a pointer to the piece of media. For the start page, we may want to exclude that table of contents. In more advanced cases, in theory, you could make use of those. But for our purposes, we can get rid of the table of contents and the acknowledgements in that first page. So we only really need to start at about page 16. And we can see that all the way to the end of the document, there's useful stuff, except for the index. The index might not be that helpful for us. So we're going to be looking at pages 16 through 513. So start page is going to be page 16, and the end page is going to be 513. So type in 513 and hit enter. The outputted column is going to be called extracted text. Now you're going to hit apply. Let's take a look at what we've got. We'll give this a second to load here. And so here we have our preview loaded, and you'll see that we have an array column, a timestamp, a path, the media reference, and the media item RID. The media reference is like a pointer to the piece of media that we started with. Here we have the extracted text. This is an array. It's an array because in the array, we have one element for every page. We have a couple of choices at this point. Given that we have an array, we're going to have to do something with it. Your choices for dealing with the array in this case are going to be either to smash it together into one big string or to explode it into all of its pages. The benefit of exploding the array into the pages is that then you can keep track of which information came from which page. To illustrate the possible trouble with that, I'm going to click into the PDF and show you. Looking at the input media, if you look at the document and scroll well into the content, you'll see that oftentimes, as we would expect with any piece of text, you have sentences or ideas that spill onto separate pages. And that is pretty typical. We see that a lot in documents. The problem here is that if we divide everything out into pages, when we ultimately chunk the document, that means that this sentence and its counterpart on the following page are never going to see each other again. And so if we have any hope of keeping, say, a sentence like this one together, we might not want to actually break this up into pages. We will break it up eventually by chunking, but the argument against separating it into pages is that we might split up sentences that shouldn't be split up. So in this case, instead of exploding that array out into pages, we're going to actually search for join array. Click on join array. And the array to join is going to be extracted text. So when we say join array, what that means is we're converting the array into a string by concatenating all of the array elements. The separator here, you're going to click on value, type in nothing, and then hit enter. The resulting column, instead of array join, should be called extracted text. So we're overwriting that original column. And hit apply. If you look at the output table, you'll see we now have extracted text as a string. Now that we have a string, we're going to chunk it. Now that the next step is going to be to chunk the text, let's talk about what chunking means. So chunking simply means to split up this text into smaller pieces. Why do we do it? So there's 2 reasons. One reason is that the next step here is going to be to put the text into an embedding model to compute embeddings. We'll talk about what those are in a bit. But embedding models have a context window. There is some maximum input that they can take, and we don't want to go higher than whatever their context window is. Now, the context windows of embedding models aren't that small. Some of them have 500 tokens, which are pretty small. Some of them have 8,000 tokens. But moral of the story, we can't just put the entire PDF in because we're definitely going to be exceeding the model's context window if we put this entire PDF in. The other reason why we chunk has to do with retrieval. Ultimately, we're processing this PDF to support a retrieval workflow. When a user answers a question, we want to be able to retrieve the relevant parts of the text, which we'll do using the embedding model. But when those pieces get returned, we want to make sure they're actually relevant. If you have an encyclopedia, and I ask you a question like, what is the biome for a chinchilla? I don't want the entire encyclopedia back. I probably don't even want a whole chapter. More likely than not, I want maybe a page, but even more likely, fractions of a page. So when answering a user question, you want to make sure that you're returning an appropriate amount of text. In order to truly understand the last reason why we need to do chunking, you have to understand what an embedding is. So an embedding is a vector representation of text. So we take text and we represent it as a vector of numbers that captures the text meaning. Now each number in the vector encodes some feature of the text meaning. And then the position of that vector in space can capture semantic relationships. So for example, if we took the word latte and we took the word coffee, they'd be pretty close together in high dimensional space. But if we took latte and airplane, they'd be really far apart. And so embeddings allow us to essentially objectively ascertain the difference or the similarity between words, phrases, and text. And the other thing to know about embeddings is that when you run some text through an embedding model, it's going to produce an embedded vector that is going to be a standard length. So sometimes it's 1536, depends on the model, which means we only have so many features that we can use to describe the text. And if the text is really big, even if it's within the model's context window, the meaning can get a little bit muddled. So the other objective of chunking is to really get bits of text that convey an idea, but maybe not more than that. But you do want to make sure that they're able to at least convey an entire idea. So tangibly, what that means is that we probably want either small paragraphs, sentences, groups of sentences, probably not full pages, definitely not words, because words aren't really going to convey a full idea. So for the chunking that we're going to use, there's a couple of different ways you can chunk. But in this case, we're going to use Pipeline's built-in chunking operation. So if you click on Search Transforms and Columns and search for chunk string, click on chunk string. So this chunk string operation is going to chop up our string into smaller pieces. First thing we have to do here is specify an expression. The expression is going to be what column are we chopping up into smaller pieces? In this case, it's going to be extracted text. For the chunk size, this is typically measured in tokens. Right now it's 256. I find that tends to be a bit small. So I'm going to change this to 512. For the chunk overlap, this allows the chunks to overlap in content. Sometimes this can make the chunks more coherent. Here we have some default separators to chunk on, so it's going to try to keep together paragraphs, then sentences, and then words together for as long as possible. So this is going to be a fine thing to try right off the bat. Going forward, of course, in your semantic search workflows, if you're noticing that your responses aren't very informative, or maybe they're returning too much information, you might want to change your chunk size or even investigate more advanced chunking algorithms. The output column is still going to be called extracted text, and we're going to hit apply. Now, if we take a look at the output table, you'll see that we once again have an array, but this is not like the array that we started with. The array that we started with was chopped up into different pages. This array, the elements represent different chunks. Now, we're not going to want to work with an array, and so we're going to explode this array so that we get one row per chunk. The next operation you're going to do is going to be an explode. So we're going to search for explode array with position. Explode array could work, but the reason we're going to do explode array with position is because that is going to retain the position from where we pulled the element in the array, which is going to give us a nice natural primary key. The array is going to be extracted text, and the output column, you guessed it, is going to be called extracted text, and hit apply. You'll have some number of rows that you're previewing, and you'll see that we have a struct. The struct has two fields, the position and the element. So the position is like the chunk number, and the element is the piece of text that represents the chunk. The next thing you're going to do is extract those struct fields. So search for extract many struct fields. The struct is going to be extracted text. And the locators, we're going to have position, which we're going to call chunk number. And then the next one is going to be element. And that one's going to be called, you guessed it, extracted text. Hit apply. And now we have chunk number and extracted text. Hovering over, at a first glance, we can see that these more or less look like complete ideas. Maybe they're a little short, but that's something that we can always revisit. Now that we have extracted text and chunked, we're going to hit apply and close, and then in the next transformation, we're going to compute our embeddings. Starting from extract text, click on transform, and call this node compute embeddings. Next step, you're going to compute embeddings. So search for text to embedding. Click on text to embedding. The text column is going to be extracted text. In the model, you have 3 options here: text embedding Ada2, text embedding 3 small, and Snowflake Arctic embed medium. I typically use either of these first 2. This one has a smaller context window, so just be mindful of that. I'm going to choose text embedding Ada2. So this is a pre-trained model, and it's trained on a huge amount of language. And that's why it's able to take text and produce a vector where the vector captures the text meaning. So now we're using a pre-trained model to do inference effectively. Now, the important thing to be careful of here, by default, the embedding is getting stored in my extracted text column. The reason why we can't have that is because we still need to retain the original text. The embedding property, the vector of numbers, is just used for retrieving the right text, whereas the extracted text, the plain English text, is what we're going to feed to our LLMs for them to use that to generate their answers. So we must retain that plain English text. Call this one embedding and hit apply. At this point, we've computed our embeddings, and you'll see that we have a vector of numbers. You'll also see that Pipeline Builder knows that this is not just any array, this is a special embedded vector. More on that later. And if you haven't renamed this path yet, you can rename it now to compute embeddings. Now we're almost done. So at this point, you're going to hit close. And we have all of our transforms. Now, of course, this result is not available to use anywhere else in Foundry yet. So to make it useful in the rest of Foundry, we're going to have to produce an output here. There's a couple different ways to do this. One option is you can add an output and make it a dataset output and then create your object. In this case, we're going to start from compute embeddings, hit add output, hit new object type. So we're skipping a step. We're making this object type directly from Pipeline Builder, which saves us a little time. You're going to type, so Gena, or your name, FAA chunk. So every object here, every instance of the FAA chunk object represents a single chunk of text from this document. For the icon, I like to do a document for anything PDF related. I'll do a document, and I can change the color if I like. Let's take a look at the properties. We're already going to have a problem here. Media item ID has been set to the primary key by default. That's not going to be a good thing because media item ID is not unique. In fact, we have the same media item ID for every row because every row of this dataset came from the same PDF, which will have the same media item ID. Instead, we're going to make chunk number the primary key. So hit the 3 dots and hit set as primary key. For the title key could be the extracted text. It might be a little bit long, but it should be fine for us. Let's take a pause here. Why are we even creating an ontology object? The reason we're creating an ontology object is that by being in the ontology, we're able to use these chunks in applications like AIP Logic, AIP Agent Studio, and Workshop. And so that is the benefit of us creating an ontology object. If you're seeing this little error on your chunk object, don't worry about it. We will fix it later. For now, let's take a look at this embedding column. You'll notice that the type here is embedded vector. So Pipeline Builder is pretty smart and knows that this is an embedded vector. We'll check this out in the ontology to investigate some special configuration that you might have to do yourself if you don't create this object as a Pipeline Builder output. And you'll notice that media reference is also a special property. It is specifically a media reference, which means it's going to be associated with the piece of media that this was derived from, which is the PDF. And now that we've configured everything, you're going to hit save and deploy. And we're going to get an error. That's okay. So click on errors. We have 2 things that we need to resolve. First, we need to hit Open Output Settings. So because we're creating an ontology object, we have to associate this with a specific ontology. So hit Save. So the second error, we're not really going to need to change anything here. You're going to have to hit Save, and it went away. So not a real error, and we're safe to deploy our pipeline. Hit Deploy Pipeline, and we're going to hang tight while this is deploying. In case you're wondering about these warnings, this is just warning us that the embedding model is computationally expensive and that we might get rate limited. Don't worry about it for now. We're going to hang tight while this is building and while the object is indexing, and then we're going to go investigate it. And now our build is finished. Let's take a look. If you right-click on this final node here and hit Open, we're going to hit Open in Ontology Manager. So open that up. Now we're in Ontology Manager. The object has been created, but you'll see that there's indexing happening. So this is the process by which the data is actually making its way into the ontology backend. If you click on data sources, you can see the progress of this happening. We're almost done here. We're just at the indexing process. What's more interesting, if you click on properties, notice that embedding and media reference are indeed special properties. Embedding has that vector icon, and if we click on it, notice that the base type is a vector, so that was correctly inferred by Pipeline Builder. But if you're creating a data set that has a vector and then creating an object manually, just double check that the base type is actually a vector and that the embedding model is indeed the embedding model that you used. Don't worry about the dimensions or the similarity function too much. When you choose an embedding model, if this is for whatever reason not done for you, make sure you click Language Modeling Service Model, and then for the embedding model, it's going to be OpenAI Text Embedding 8.2. But what's most important is that whatever embedding model you use to create your embedding, you specify that exact same one here. The reason they must be the same is because in front-end applications like AIP Logic or AIP Agent Studio, when a user asks a question, that question is going to be translated into an embedding using the same embedding model that is specified here. And if that's a different embedding model than the one that you used in your pipeline, you're going to have some very weird results. Now our index process is finished, and we're ready to go use this in applications like AIP Logic and AIP Agent Studio, which we'll do in the next video. Thanks for watching. We hope you found this helpful. Let us know what AIP questions you have in the comments.